Hi there, my name is Jackie, and today I'm going to take you through the synthesis of ibuprofen. As you can see, we start off with a carbon chain attached to a benzene ring with an ester group right here attached to that alpha carbon. Our product, we have the carbon chain remains the same as does the benzene, but instead this alpha carbon now has a methyl group attached to it, and this is no longer an ester, it's now a carboxylic acid. So how do we get there? First, we're going to use our first reagent, which is sodium ethoxide. This is going to dissociate, leaving Na plus and OET. That oxygen is going to have a negative charge. It's going to take these two electrons and deprotonate this alpha carbon right here, which is very acidic. It's going to kick these electrons back onto that carbon right here, forming our carboxylic anion. And here we have ethanol floating in solution. That carboxylic anion is going to react with our second reagent right here, which is going to be our ester group. These two electrons are going to attack the carbon on the carbonyl and kick these pi electrons onto the oxygen, forming a negative charge. Right here we have our tetramethyl intermediate, and our enolate is going to tautomerize into its more stable keto form. So these two electrons are going to kick back to that carbon, forming a double bond between oxygen and carbon, and as that double bond is formed, this ester group is going to be kicked off, and that's going to be our leaving group. That leads us to our first intermediate, intermediate A. Here we have two ester groups attached to that alpha carbon, and we also have sodium hydroxide floating in solution, sodium ethoxide, excuse me, floating in solution, and we have that B dicarbonyl compound. Here, for our second step, we're going to use sodium ethoxide again. We're going to take these two electrons off that negative oxygen and attack this even more acidic alpha hydrogen due to the compound. And we form our carboxylic anion, and here we have ethanol floating in solution. That carboxylic anion is going to go ahead and attack this partially positive carbon, which is attached to our iodine. Our iodine is slightly negative, which makes that carbon partially positive. So as that carboxylic anion attacks that carbon, it's going to kick these electrons onto that iodine, which is floating in solution. So that brings us to our second intermediate. Here we have two ester groups along with a methyl group attached. For our last two steps, we're going to use hydrolysis as well as heat. The two electrons on this oxygen of this ester are going to grab this H plus floating in solution, giving us an alcohol group up here. These two electrons on this water molecule are going to go ahead and attack the carbon off that carbonyl right here, kicking these pi electrons onto the oxygen, which as you can see is hungry for electrons with that positive charge. Here we have our tetrahedral intermediate. We have an alcohol group, an ester group, and a water group right here. So the two electrons from H2 are going to attack this hydrogen on that H2O molecule, kicking these electrons onto that oxygen, which as you see are hungry for electrons with that positive charge. Here we look at our tetrahedral intermediate again. Now the two electrons off of our ester group are going to attack the hydrogen floating in solution. Now we have an ethanol group, and we have an alcohol up here. The alcohol is going to tautomerize, which involves these two electrons coming back down to this carbon bond, forming a pi bond. As that pi bond is formed, as that double bond is formed, this ethanol group is going to be kicked out. That's going to be our leaving group. Here we have water coming in again. It's going to deprotonate that alcohol, kicking those electrons to that oxygen, getting rid of that positive charge, and here you can see we have our carboxylic acid. We're going to repeat that same process for this ester, which results in two carboxylic acids with a methyl group attached. For our last step, we're going to use decarboxylation or heat, which is loss of CO2. The electrons between the oxygen and the hydrogen are going to kick back and form a double bond between the oxygen and the carbon, which is going to leave the electrons on that carbon right here. So our CO2 group will be leaving now. And now, as we see, we're finally at our final product, which is one carboxylic acid group. We have a hydrogen right here and a methyl group right here. And here, one more time for clarification, our carbon chain remained the same as did our benzene ring, but instead we have a methyl group and a carboxylic acid. Thanks for watching. I hope you learned something. Go Knights!